Okay, let's start. Is everybody here? Seems good. Okay. Today I'm gonna give you a quick introduction to Nix. So we're not gonna do a whole lot of coding, unfortunately. But unless you understand the basics, it's gonna be pretty difficult to grasp what it's all about. So I'll start with a little bit of history and what the goal of the Nix project is. So if you think about deployments, it's all about getting the tool or the application that you want to have where you want to have it, and also to get only that to where you want to have it, because otherwise you have stuff that is unrelated and might interfere and also poses security challenges. And you also want to make sure that your deployments are as fast as possible and as reproducible as possible, and that everybody gets the same results if they follow the same steps. So the history of this whole tale of deployments starts with the configuration management, and before that we had the no management part where everybody just SSH'd into a server and ran some apt-gets. And after that, Chef came along and revolutionized the space, basically, where you set Chef recipes that run sequentially, and once it's stopped and you write a new recipe, that will start again at the point you stopped last time, and it doesn't really care what happened in between. So what happens with configuration management software is that often you end up with relics from the past, where you have configuration files or programs or debugging output or logs or things like that lying around that you really don't want to have anymore. But discovering that you have it is going to be pretty difficult. So what people came up with is the layer management model, which is what Docker is all about. And that was yet another seemingly awesome revolution, where everybody can build images and distribute them like VMs from the old days, but much lighter. So you don't have to download a gigabyte, you have to download a few hundred megabytes. The thing that layer management does is that you start with an empty layer, and from there you add all the build products that you want to have into your layer, and you usually also build them inside of the container. So the build is also reproducible, as long as all the dependencies are still available on the internet, that is. And otherwise you have to implement some caching strategies, like we do at Xing, where we have our own Ubuntu cache, where we cache pretty much the whole repository. And we also have our own Docker registry, where we cache all of the images that we have built so far, and also use that for deployment. But the individual parts that go into the image are usually not cached. And that means we have to download that part. And the other part is that once you start diverging in a layer, all subsequent steps cannot be merged again. So you cannot really reuse any of the image parts from another image. Well, not easily anyway. So if you have an image that is built for deploying Rails applications and you have one that is built for deploying Go applications, you end up with no common steps after that part, even though you just installed one package additionally. And that means you cannot really share any of the load between different projects or between different departments or between different CIs. It all has to be done from scratch again. So the other part that you end up with is that some of the development tools end up in the final image. Like our Xing images all have a shell. They have compilers installed. We have different configuration files that aren't really needed. We basically have a whole OS inside of the container, and that is not really ideal, because in the ideal scenario, you only get in production what you actually want to run in production. So that is what you're probably all familiar with. If you're not familiar with all of them, please ask questions about them, because now we go to the next step, which is gonna be the graph-based approach. So we had the node management, the configuration management, the layers, and the graph-based approach is the one that I want to talk today about. And I don't think there's any system other than Nix that implements this correctly and fully, and is also has such a strong community at the moment. So graph management is basically you build a graph out of nodes, which are your build products, and then you only put this node into your final deployment, and you build them independently. So they cannot influence each other, and you can basically share all of these products, and then you just put them into an image, or you put them on a server, or you put them into your development environment, or you put them, I don't know, in binary cache. The way that development works with graphs is that you have a lot of distinct parts that are built separately and that you can then reference separately. So if I want to compile an application, I'm going to need an editor and I'm going to need a shell, but the deployed environment doesn't really need that if I am not going to run shell scripts there. So the only thing that I want to copy there is going to be the compiled app and any binary dependencies that the application has. And that is not as prevalent with Ruby because it has a whole load of dependencies. So you end up with like 300 megabytes at minimum. But for a Go application, all of this stuff is basically overkill that you get in a standard container. You only want to have one static executable, and that's it. And the source code also should live at the developer, but it shouldn't really end up in any of the previous production deployments. So that's what I'm going to talk about as well. You also don't really care about the dependencies that your tools have, but you want to specify exactly the dependency of the tool that you want to use. So it's reproducible between all of the different development environments that people use. This is a small example of a Ruby application that is built with Nix. And all of the inputs basically are specified from the gem file. Then the bundler creates a gem file lock. Then the Bundix creates a gemset Nix. Then that goes into a bundler environment, which also requires a version of Ruby. And that version with Ruby is then built with all of these dependencies already in the right library paths. So it doesn't need to do any dynamic lookups at runtime. And you also add any of the binary dependencies that you want to have during the runtime. So these are transitive dependencies that are going to be available, but you don't want to have ImageMagick in your main path if only AirMagick is using it. So that's basically what this is about. And this graph could be expanded arbitrarily because you need to have some tools that compile your libxml and libiconf and stuff. So yeah, this slide is a bit too small. The goal that I want to show today is how we can, first of all, distribute the load of building all of this stuff. Second, how we can get all of this to the developers and into continuous integration, and then only the stuff that we care about into our deployments. From one common shared Nix store, so you don't have to build things over and over again. And also, so you don't have to build stuff yourself, we can use more powerful machines for that. Any questions so far? No. Okay. So what Nix is about is basically build a graph system of all your dependencies, so you can pick and choose which part you want to have, and every time you pick it, you get exactly the same result again. What it used for this is functional programming, which in the case of Nix is based on the lambda calculus. So it's a language that has no side effects, no mutable variables, and no loops. And it was, wait, I'm stuck here. Okay. So it was developed in 2004 by a guy at a university in the Netherlands as part of his PhD research into a safe and policy-free system for software development. And the language hasn't changed much in between. So you can still run the same programs that were written back then, today, more or less unchanged. So there have been a few functions added, but the core of the language behaves the same. Based on that, the NixOS operating system was then built, which builds the whole operating system using Nix and then uses Nix as the package manager as well. And that project has been going on for, I don't know, maybe now 10 years or so. So it's also quite reliable and stable these days. And I've been using it for the past 3 years every day. So that's my main development machine. And I also use it on my notebook. Nix is basically reliable. We already talked about that. Reproducible, great for developers because you can share your environments. It supports multi-user installations and multi-version installations. So you can install the same package in multiple versions alongside each other. And every user can have their own environment, even on the same machine. What that means is that you don't share a whole set of packages across the whole operating system, but everybody has their own view that they want to have. And this can change even if you just change a directory. You get a different view. It supports it's based on the source and binary model. So you build everything from source and then you cache the binaries. And that means you don't have to build anything twice. You can just fetch it again from the cache. And it's also portable. So it runs on Linux, macOS, BSD, now on Windows 2. It runs on Raspberry Pi and pretty much any router or whatever else you want to give it. There's probably a project that supports it. So the reliability from Nix is every time that you install a package, it gets written into an immutable store, and then you only link to a reference of it. And that means that if you install a new package or you upgrade a package, it will not change any of the existing packages. It will just be, well, reliable. So you can always go back to a previous version if you want to. It just means you switch one symlink. Okay. Since switching symlinks is atomic, you can also use it for deployments. So with one move command, you can upgrade to a new version of your whole operating system. It's reproducible because all the packages are built in isolation from each other in sandboxes. They don't even have unchecked internet access in there. So every time you want to access the internet, you have first to specify what you want to get from the internet in form of a hash. Then it will download it, it will check it against the hash, and only then you will get access to it inside of your package build. Also, all of these downloads are cached in the Nix store and hashed properly, so you will not download anything twice. that also means you will never have undeclared dependencies, because if you try to use one, it will simply break the program and it will not run. So what is really nice about this is I can just copy a package to another machine as long as it's the same architecture, and it will just work the same. It's really great for developers, so I love it. That's one of the main reasons why I use it. Because you can set up your build environment, and then you can share it across projects. And every time that you go back to a project, you can get back into exactly the same state that it was before. So even if I haven't touched a project in 2 years, I just go there, it will download all the old dependencies, and I'm back to where I was back then. And that means I can also then work on upgrading all the dependencies one by one and still check that it works, and otherwise roll it back. A nice example for that is if you just want to develop, like you want to build Firefox, you can check out a Nix shell for Firefox, and you get all of the dependencies that you need to have for it. This one we already talked about, so I'm not going to elaborate on that very much. One nice part is that you don't need root privileges to install the software. So what Nix provides is a build daemon, and you talk with the build daemon, and it builds for you, and puts it into the store. And once it's in the store, it will tell you, and then you can use it. So you don't have write access to the Nix store, only the build daemon has. And that means that you also cannot write accidentally from your programs into the Nix store. Which also means that you cannot change any of the existing packages, even by accident. The source binary model, yeah. So you're probably familiar with Arch Linux or Gentoo. Yeah, you know Gentoo. That is based on the source model. Arch Linux is half based on the source and half on the binary package management. Things like Ubuntu are only binary package management. So if you want to build something from source, it's always an ordeal. And Nix basically combines the both. So if it doesn't have binary, it will build it for you transparently. It will just take a bit longer, but the result is going to be the same. It's portable. Yeah, we already talked about that. So yeah, we can start with the programming language itself, or I would like to take any questions that you have.
Yeah, so basically, if I understood it, the idea behind it is that basically your file system, it works with nodes as an immutable data structure. So every time you change it, you don't change the original structure, but you just add a new node and point this node to whatever the old structure, so you replace the nodes that you want. But
Exactly.
That's only your view, right?
Yeah. So it depends on what symlinks you have in your path.
Yeah.
That decides what binaries you can execute at the moment.
Okay. And then
that is also transitive.
And the other thing is, you said that the same package would work seamlessly regardless the operating system, as long as you have the same architecture. That's right?
That's for Linux, that is true.
Okay.
For Darwin, the kernel is closed source, so that's not really possible at the moment.
Okay. So it works regardless of distribution.
Yeah, so I would not consider Darwin the same architecture. I mean, they use the same CPUs,
Exactly.
But the whole userland is completely different.
Okay.
And you cannot replace the kernel.
Okay. Okay. So it's not only the hardware architecture, but also the operating system as well.
Yes. So it doesn't replace your OS. It still has to talk with the kernel, and for that it needs syscalls.
Okay. Understand. Okay. It was a little bit of a weird, then I understood it wrong. Okay. Because it was
Yeah.
weird. Wow.
But usually you can still use the same build instructions that you give to Nix, and it will still build it on Darwin and work.
Yeah, but the binary itself, it won't be portable anymore. It will only work on Darwin.
Yeah, because macOS is not binary compatible with Linux.
Yeah, makes sense. Yeah, understood.
Can
Okay.
you port it to FreeBSD if you build it on macOS?
No. They haven't used the same kernel in a long time.
But they have the same userland, right?
I would debate that, but yeah, it's like an ancient version of BSD that they're using.
Okay.
So yeah, usually you still have to rebuild stuff between the systems if they have too different of a kernel version. But you can also specify exactly which version you want to have in your build instructions. So, yeah.
So right now it would be an issue if most developers have Macs, right? Like adopting.
No. I mean, basically, there's a build form for Darwin already, which uses, I don't know, like 10 mini Macs, and they build the whole Nix packages repository every time, as far as it's possible. What we can do is, as long as we have a build machine that runs macOS, we can still run our builds and then cache them.
Yeah. So basically, what it does is you keep the same syntax. Both the building instructions for your operating system is Nix anyway.
Yeah.
And that internally translates to getting the source code and compiling it in your machine. And that's it. So in order to have it portable, you can just have a somehow shared cache among all of us. It's in the internet, or that's distributed or somewhere else. So you can, when you want to have it, it gets the binary, it get it from there instead of downloading the source code, right?
Yeah, we could have a Xing internal cache that works for all our developers, and that can then be reused by everybody.
Yeah.
The other option is, since we deploy to Linux at the moment, that we run a Docker container on the Mac and then build everything inside of Linux.
Yeah.
That also works.
Yeah.
So or that's what I've been using.
Yeah.
Yeah, or you have a Linux machine around, but most of our people don't.
Yeah, or a virtual machine. Don't even need a container. You can do, because in the end, a container in Mac, it runs inside a virtual machine anyway.
The xHive doesn't. So they have native extensions for virtualization now in the kernel. And that's what Docker is using. So if you use a virtual machine, it's going to be slower still.
Okay, understand.
Yeah, at least that was the state that I remember from half a year ago. Maybe the virtual machines got better, but last I tried VirtualBox, it was even worse. Yeah, so that's basically about the build. We can go to the syntax now, otherwise I'm going to run out of time. There's only 5 primitive types in the language. So you have ints, you have bowls, you have paths, strings, and floats. And the only thing you don't know already is the paths, I would say. So the ints work as you would expect, I think. Then we have the booleans, where you have true and false, and you can do Boolean operations with it. Then we have the paths, where you can reference any path that you want to have. and you can also combine them to build new paths, or you can get relative paths. Every time you reference a path, it will store the original location in any subsequent manipulation that you do with the path, and that means it will then be a dependency of your build. So it will end up in the final result, and that means you can then copy the package to other systems and it will still work. And we have the strings. So that is a normal string, that is string concatenation, and this is string interpolation. It's pretty similar to Ruby, I would say. Then we have floats, which also work pretty much normal. And the composite types, which is where the interesting stuff begins, since it's a functional language. And it's looks a bit like JSON or maybe Haskell. Yeah, like a mix of these two. But it predates Haskell as far as I can recall. So the syntax for the sets is keys, and then you have values. And if you want to have spaces or special characters in your keys, then you put them in quotes. If you don't, then you can just use them verbatim. And you can access them with the dot operator. So this is not a method call, it's access of an element in your set. And keys cannot be duplicated. That's where the name set comes from. And you can also merge sets. And the right-hand side will take precedence. So if I have a count here and a count here, then I will end up with the count of this one in a new set, which is the result here. Is this... Did everybody understand that? Probably yes.
Yep.
Yes.
Otherwise, just talk up.
Yes.
Okay, we have lists here. In lists, you can put any other object. It's, what do you see, heterogen? Yeah, I think that's the right word. And lists are lazy data structures, as well as sets, but I didn't really show that there. If you put nested lists in here or sets in here, they will not be evaluated until you try to access them. And that is an important property of Nix, because it doesn't try to build anything that you don't try to reference. And that means all your build instructions can live in the same repository. And as long as you don't try to access one, it will not be built, and it will not end up costing you any time. Yeah, I think that is also, here is a function call. I'll explain functions on the next slide a bit better. This one takes 2 arguments. First the list, and then the index that you want to access, and then you get the list back. And this is a function call with 1 argument, which is just a list. Then we come to the lambdas. So in lambda calculus, every lambda only has 1 argument. And in Nix, you also only have 1 argument for each function. So if you want to take more than 1 argument, you can either use this approach here, where you take a set as an argument, or you can take another approach is where you nest 1 lambda into another. So you first pass 1 argument and you get another lambda back which has this argument already. And then you pass the next argument and then it will finally evaluate. You can also specify default arguments using the set structure. So if we don't pass the m here for the increment function, then it will automatically increment it by 1. So far, I think should be clear. No questions. Good. So there's quite a lot of built-in functions. This is just an excerpt where you basically have methods to fetch Git repositories or Mercurial or tarballs or arbitrary URLs. You can read JSON files or output JSON files. You can check types of arguments, all the good stuff, basically. And if you just call this one in an Nix build, then you will see all of the built-in functions, so you can try them. To summarize, the packages we define as Nix expressions, which are functions. We get atomic upgrades and rollbacks. We can have multiple versions of the same package in the same system without impacting each other. Unprivileged package installation. So you don't have to give a user sudo so they can install the package. You can manage user environments and have isolated environments which play into the user environments. So I manage all my dot files and all my packages and software that I use using Nix. And that works very well. So I can just distribute it across all my machines and they work the same. We get reproducible builds from source if we don't have the binaries available. We can cache the ones that we built, so we don't have to build them ever again. And we have safe garbage collection. So once we remove the link to a package, it will then be safe to collect the garbage for it and delete it from the store again. That means as long as you have a reference to a package and you're using it in production, it will not be garbage collected. Which is quite a big bonus if you are worrying about sources going down or repositories changing or things like this. And right now, the Nix packages repo has about 40,000 up-to-date packages, and I think about 800 are outdated, with 830 maintainers. Most of the updates of packages are now automated, so it doesn't require that much manpower other than reviewing each package and check that it is actually a good update and that it's a wanted update. Okay, so some links to start with. I actually put this presentation in the internet, so you can see it here. I'll paste it in the channel. Yeah, where was I? That's when you want to get a bit more information. But since we're a bit early, I think you can actually start looking at some Nix expressions, and I can explain you a bit more about how the build process works. Is that okay?
Sure, yes. Yeah.
Yeah, cool.
Go for it.
Unglaublich. Great. This is probably too small for you guys.
Yeah, if you can zoom in a little bit, that would be great.
Is that better?
Yes.
Yeah, much better. Thanks.
Okay, and also make it white, maybe. So nobody can complain anymore. So this is also all in the repository that I shared the link to. And I'm gonna look at the first, wait, why isn't that? I have to zoom the frame. So basically what we have here is a simple derivation. It's not super simple, but it's quite simple to explain right now. So this one takes two arguments in one set, which is the standard environment. That is one of the packages that you get from Nix packages, and fetch_ul, which also comes from Nix packages. What we do is we make a derivation, then we specify a recursive set. That means values inside of this set can reference other keys inside of this set, which we use here for the name. So this name can reference to this one. If we don't do this, then we get an error. So we specify the name of the package that we want to have. We specify the source where we want to download it. And we also have to give the checksum of what we expect the source to be. And then we specify that we want to run the tests for this package as well. Yeah. And this is gonna be a little bit uneventful because I already built it. So I'll also explain this command here. I call nix build with show trace, and then we evaluate an expression where we import the nix packages that we specified. I will show you that in a bit. And use a function called callPackage on the current directory with no arguments. And when I run that, then it already found that I have hello in my binary cache, and it returned it to me. What it also did is it made a symlink for me, which is under result. And this result will then point to the path in my Nix store where this whole package is. So what we get here is every dependency that this package needs at runtime, plus the info page, and also the locals for the info page. If we want to not have the info page, no, I'm not gonna go into that right now, but I will explain that if we have another session, because multiple outputs is also possible from one single package, where you can have variants of the packet and they still can share the same source. So if I want to run this, I just run result bin hello, and it will output the hello. And then we can also say like all equals like JP, and no? Oh, sorry, I have a typo. Why? This used to work. Yeah. So this one works. Ah, never mind, because I removed the locals dependency from the package, so I cannot look them up again. This is not the original package. I simplified it quite a bit. So it lost support for multiple languages. If we look at the original one, that looks like this. And it has a bit more configuration. So every time you want to look up a package, you can just jump there using this one. So we can look at the description for Firefox, for example, and check what are the dependencies of Firefox and how do I actually build it. And then it will go and build it if you want to. So what I could do is nixshell f Firefox, key Firefox. That would give me a Firefox in my shell. And the other one that I could do is, let's say we want to have Nix packages current one, and then get a shell for Firefox. Then it will download all the dependencies that I need to have. So it's like half a megabyte. And then put me into a shell where I have all of the dependencies that I need to have. So right now it's a bit messy, but if we specify pure, it will actually remove my existing system and only put into the path what is needed for this package. So what we have here is we don't even have a bash here. Oh well, let's go on, because that is not super important. What is also nice is you can write derivations in other languages. So what I do here is I have a derivation that I implemented fully in Ruby. If you look at this one actually uses standard environment, make derivation, which uses bash as the default. So if I want to write scripts here, they have to be in bash. What I can do here is I can specify a builder, and then the arguments that are passed to the builder. Let's make this a bit more obvious. And the source we put here. Okay. And I can also specify that I want to have a Ruby that doesn't really have YAML or curses or GDPM or OpenSSL. We don't care about this stuff, so we will not build it. And that means the Ruby is about 100 megabytes less fat. And then we put this slim Ruby into our path. And then we call the builder with this argument. And this is just a standard Ruby script. So we require file utils, we split the path, fetch out all of the elements from the path, all the executables. Then we get the environment variable out, which is provided by Nix. And this is where I have to put my output. It's basically the path that matches the hash that my inputs had. And then the hello binary, which I will produce. So I open the hello binary, I write stuff in here. I open the source, which is the source that we specified here. So it's just another Ruby script. And then we go over each line, check for a shebang, and replace it with the paths that we have. That way, we can make sure that Nix also finds the dependencies for shebangs in our Ruby scripts. So if you look here, we have user bin and Ruby. But on a deployed system, we cannot be sure that Ruby is in the path. So what we do is replace it with the executable that we told Nix to use. So if we go into the Ruby derivation, and we build also this package, then we have the result bin hello, which outputs hello world. And if we look at it, it's not the same anymore. So this is a bit stupid. I should probably fix that. But right now I only replace the shebang like this. But what I should actually do is this. And I'll build it again. So let's make sure it still works. It still works. And our shebang is now standard. So we actually don't depend on user bin env anymore, but we only depend on Ruby. Yeah. Okay. If we look at the closure size of this result, it's 317 megabytes because it includes Ruby, and Ruby is pretty big. So if you look at all of the dependencies of our result, GQ, then you will see, let's select only the paths. Wasn't that? Here on this path, right?
So, Michael, if I understood it well, basically the derivation, what's the name? Derivation, derivative, derivation. A derivation?
Yeah, the derivation creates a derivative.
Okay, and the derivative, it would be somehow a binary.
It doesn't have to be a binary. So in this case, the result file is not a binary.
An executable.
Yeah, but it doesn't have to be an executable anyway. It can be anything that you want to have.
Okay, an artifact then. It's gonna go one level up then.
Yes, we can say it's an artifact.
Okay.
So if I show you my Nix store real quick. Sorry, that's going to take a little bit. Then you see that everything that is on my system is actually in the Nix store. So if I look,
derivative.
Yeah, any derivative.
Okay.
Anything that is on my system is either directly in the Nix store or symlinked to the Nix store.
Yeah. And
So
then,
if I look at CoreUtils, it also has the libexec, which has the libstandard buff. So we have all the libraries available.
yeah.
In the share directory, it has the man pages, so you can look at all the documentation. You get all the locals, you get the messages in your language, stuff like this.
And how it is that you make reuse of different parts from one derivative to another? I didn't get exactly what's the way. You do it via path?
Yeah, usually it works over paths. That's pretty much the path type what it is for.
Okay.
So I don't have a path type in Ruby, so I have to emulate it. But Nix supports that natively. So if we look at, let's see, I have a greeter here. That is another example that I built quickly yesterday. Here we have dependencies. Wait a second. For example, here we depend on the GNU Hello program that I showed you before that generates all of these messages. And if I depend on this, then it will be a build time dependency. But if my resulting program includes a string that points to the Nix store, then the path in the Nix store is going to be a runtime dependency, and it will also be in the derivative, and will be a hard dependency. And that is how I got, that's why I transformed the shebang. If I can show you the Ruby derivation, what was that? The builder RB. So if we remove this and we don't check the shebang, what do you think will happen?
That it won't work because it doesn't have the binary.
Well, in this
Doesn't
case,
have Ruby inside.
yeah, but in this case I have Ruby in my path, so it will still work.
Okay.
Because it uses environment lookup, and Ruby is in my path.
Okay. So yeah, it will look for, and it works just by chance because you had Ruby there.
Yes. So if I look at the dependencies of this new package, it will only show that it depends on one file, right?
Yeah.
It only depends on this text file, and that's it.
Yeah.
So it only has 528 bytes.
Yeah, obviously, just the file itself.
Mm-hmm. So Nix is smart enough that during runtime, it checks all text files and all binaries if it has a reference to the Nix store path, and then it will add it as a dependency for me.
Okay.
So I add it back again, I build it again, and since I already have it, it doesn't really have to build anything. So that's how the dependency management works. It's quite implicit.
Mm-hmm. Still getting my hand around it, but I think I got more or less the idea.
Okay. I can now show you how you can do dependencies inside of Nix derivations. So what I did here is I have a function which takes 4 arguments. Again, the standard environment, the fetch_ul. We also take bash and the glibc locals. And then we specify a set for the languages that we want to have, alongside with the local that is the glibc standard. Then we import another function and call it with the standard env and fetch_ul. So if we take a look at hello default, you see that the names here have to match. And then we specify a function called greeter, which has two default arguments, which is English and English local. And here we make another derivation, which means we want to have this part here in the next door. We call it by the language with greeter on it, and we specify that it will only have an install phase. We don't want to build anything really. And that we want to have the native build inputs, so they will not be propagated. And an install phase. And the install phase is the script that actually runs when we run this derivation. And what Nix gives us is, again, this out environment variable, where we have to put all the results that we want to have in the Nix store at the end of the derivation. If we put it anywhere else, it will give us an error because everything else is immutable. And the way it achieves this actually is using namespaces. So it's using Linux namespaces and bind mounts. And so you only get access to the parts of the system that you specify for your derivation. And everything else is hidden from this program that it runs right now. So what we do is simply we output this text here into a binary, and then we make it executable. It's not really a binary because we simply call our shell, but well, for this example, I don't want to write any C. And here we have our final result. So what I do here is a let, and below here we have in, and that lets us specify variables, which aren't really variable, but we can assign it, and they will not be showing up anywhere else. And then we can reuse these variables inside of the let block or inside of the in block. That lets us give multiple inputs into a single output. So what we do here is we have a derivation called hello goodbye, which only has an install phase. We have another function here called greeters, which calls map. It takes the language as an argument. Then it calls the greeter with this language and the local that we look up in the greeter set up here. And it does that for all of the attribute names in this greeter set up here. And since this is a list, Nix will translate it into a bash list and put it into the environment variable greeters. That means we can do a simple for loop over the greeters and then put them into the out bin. So far, all clear? Yeah, I guess so. Otherwise, just complain. We have 3 more minutes that you have to hold out. So if I show you the result now, we have a result directory, we have the bin directory, and inside we have hello English and hello German. And we made symlinks to them. So at runtime, we expect that these here are built already. So if I try to run them, hello German, for example, it says hello world. And if we run the English one, it says hello world. So what do you think happens when we enable more languages? What does it build again?
Since you haven't built it really, it's gonna blow.
Yeah. Well, I enabled Japanese now, and I'm just gonna build it. And this is what happens. So at the beginning, it tells me what it will build. And the only thing that it will build is the hello goodbye, because I already had the Japanese greeter built. Let me reduce the verbosity down here. Okay. And what we get now in our result is 3 executables. So if you now run the result bin hello Japanese, it will output it in Japanese. So let's enable also Spanish.
Good luck there now.
Why?
Because I thought you were not gonna build the Japanese. I thought it would blow because you said that it has to be pre-built. It assumes that it has to be built somewhere else.
If it's not built already, it will build it.
Okay.
That's the whole logic. So this is the build instructions for the greeter that we have. And we pass the language and the local to it, so it knows how to build the greeter. And then we simply symlink it. So all we have to do is reference it here. We call the function and we get the build output as a result. So I can show you, oh, we actually know where the greeters is. So this is the bash array that we get. We get the English greeter, the German greeter, the Japanese greeter, and the Spanish greeter. And then we just symlink them. We can now also add the Italian one. And if you know another local, I will also add that. Yeah. Make that a bit bigger. I need one more that I haven't tried yet, so I can show you how it actually builds.
Mm-hmm. Portuguese.
Portuguese.
Yeah. Okay.
Yeah. What language is that?
I believe
you
it's
know that?
PT_PT or yeah.
Okay. I think there's PTBR as well.
Yeah.
Yeah. Let's build that. So now it tells me it builds the Portuguese greeter here.
Okay.
And then it already installs the Portuguese greeter. And then it builds the hello goodbye with the Portuguese greeter. So we get it here. And then we can just run it here as the Hola Mundo.
Mm-hmm. Yeah.
So all the rest is never built again. It will just reuse the cache. And if I reduce it now to just one language, we get this one again. And the tree is empty. And now we can look at the Nix store and see that we still have all the hello, goodbye derivations there.
Yeah.
So I built quite a few.
Yeah.
And every time you want to go back to it, you can simply either build the derivation again, or if you use nixenv, then you can roll back. So what I will show you next is if I have a result, this time with English and German, then I can run nixenv I result. It will install hello goodbye into my user environment. So if I say, like, what is the English greeter? Wait a second. What was the name of this? Hello. Hello English. Then it will tell me it's in my Nix profile. And if I check what is the Nix profile, it will say, oh, it's in my Nix store.
Mm-hmm. Yeah. And everything inside the Nix store, it's a node, basically.
Yeah.
For the graph.
So it all points to each other using symlinks, and it builds a graph structure.
Yeah. Using symlinks and path for resolution, for binary resolution, for executable resolution.
Yeah. So I build it again. And this time, I also have the Spanish one. So I will install it again. And it will say it replaces my old hello goodbye and installs the new hello goodbye. And now I can also say hello in Spanish.
Mm-hmm.
Without specifying the path anymore. And what I now have is, God, I have a brain fart. And list generations, there we go. So these are all the generations that I have in my user environment that I already had. And what I can do is nixenv roll back. So we roll back, and then I try to run Hello Spanish, and it doesn't find it anymore because it went back to the previous state.
Mm-hmm.
Yeah?
Yeah.
And that means no matter what you install, you can just remove it again. And it's super simple.
And what happens when you change the user?
When I change the user,
Yeah, you get to another store.
no, the store is the same. But what changes is this part here. Right now I'm in Home Manvaru Nix profile.
Yeah.
And everybody has their own Nix profile. I can also show you where the Nix profile lives, because that one is also a symlink. So this one is in Nix var Nix profiles per user Manvaru profile. And if we check that one, I have multiple profiles. So I have a system profile, which is my operating system.
Okay.
We have per container environments, which are just kind of like Docker containers. They're using LXC to build containers, and per user environment. So at the moment I have 2 users. Well, I have more users now, but I used to have only 2, which is me and root and git, which is like a Git server, and the build farm, which I use for other machines. So they can use my machine so they can build faster. And all we see, what happened here? My shell just died. Okay. Nix var Nix profiles, per user. Sorry. Here, this is all of the links that I showed you before. And all of them are again links into the Nix store.
Mm-hmm.
And this one is the current one, which links to a path in this directory. So if you want to change your generation, you only have to change this symlink, and suddenly you have a totally different view on your system.
Yeah.
And other users can then change their own, basically. And the same, I cannot see the containers right now. A second.
So everything is soft links all around.
Pretty much everything consists of links, yes.
Mm-hmm.
So that's why it wasn't ported to Windows for a long time, until they added the Windows subsystem for Linux.
Mm-hmm. Yeah.
Because their implementation of symlinks was just not enough.
Yeah.
So is it better supported on Windows than on Mac?
Better on Windows than on Mac? No, on Mac it's way better, because actually people are using it.
Also, did you show how you get the SHA hash? Like, how do you find it?
Oh, okay. I can show you that as well. I can just take any URL. So I can take the URL of this index.html, for example. Prefetch URL, and then it gives me the hash for this.
Mm-hmm.
And it tells me what the Nix store path is going to be. And actually, it's already in the Nix store. So we can check what it is.
Uh-huh.
I actually built all of these slices also, all of the slides also with Nix. So you can take a look at that. I built the whole index.html with Nix, and then the file list is also generated dynamically.
So that SHA isn't tied to the channel, right? It's independent. I thought it's
no, the channels are basically just tested collections of software.
Uh-huh, okay.
So what Nix does is, if we go to Hydra, or even better, how old is I'll have to finish soon because apparently my sister just got a baby.
Oh, congratulations.
What we get here is the channel. So every time you check out a channel, you actually download this part here.
Mm-hmm.
And then it will tell you what the store paths are and what the Nix expressions are, and also where the binary cache is. So from the binary cache, you can then download all of the described expressions that are here.
Mm-hmm.
I'm not gonna download this right now because it's a bit big, but you can probably guess. This one is in the Nix path environment variable, so I can show you a checked out version. I have a link to a channel, which probably is not very surprising. And what do we have here? NixOS. Okay, that's the name of the channel. We don't care about this one. We care about the Nix packages one. So what we have here is basically a clone of the Nix packages repository. And here we have a symlink to itself, so you can say nixpackages.nixpackages.nixpackages.nixpackages and so on. And the rest is the package's descriptions, which includes, like if we check the development interpreters Ruby code Nix, you can see that it downloads a patch that we need for Nix. And then it builds the whole Ruby interpreter, and we support 3 different versions at the moment.
Mm-hmm.
And every time you want to change the Ruby version, you will first have to download the version, then you get the checksum, and you get the Git revision that you need to get the patches from. Since we also apply the, what's it called? The Rails Express patches that are maintained by one of Xing. Stefan Case, I think, makes them.
Mm-hmm.
So we apply them as well. So the Ruby is the exact same that we have in production. Yeah, but if I only reference paths inside of the same directory, then we don't really care. So what I do here is I copy the image directory directly from this path. So all the images from the presentation here are SVGs that I just referenced. And also the configuration for the slideshow generator, which is a Ruby gem, I have in the repository, and I pass it on because I modified it a bit. Yeah, so that pretty much concludes it. If you want to, I have prepared another session, but we can go into that next time. And then we can handle a bit more advanced topics, like how to actually use this for something useful other than building slideshows.
Yeah, the workshop would be like more hands-on. So it would be more.
Yeah, but for that you actually have to install Nix.
Mm-hmm.
Because yeah, I built a Nix CI that we could use, but it's not very hands-on. So you would upload your code into a Git repository, it will pull it for you and output the result.
Mm-hmm.
That's not very exciting. You could also run it in a browser, but that's a bit of an old version. Yeah, maybe if you want to just play with it, you can try that. It's on Nixcloud.io.
Mm-hmm.
They have it at the bottom under Tour. I'll also paste the link here. And it takes quite a bit to load because it actually runs Nix inside of your browser. But once it's loaded, you can use it pretty well. So I'm not going to do that here because it's going to mess up my stream. Okay, so check out the repo. It has some nice code in it. And if you have Nix, you can also build the same slideshow that I did. The result should be identical to the one that is in the docs folder.
Mm-hmm.
And how I achieve that is that here I import static checkout of the Nix packages. And I also specify the hash for it. So all of the dependencies that we have here, they're all always the same version for everybody who uses this project.
Mm-hmm.
And I also made a shell where you get this gem, so you can run the slide gem command interactively. And I also have Bandix, so you can update your gems if you want to. So that pretty much wraps it up. I really have to leave now. Sorry, folks.
Thanks for the presentation and Mazel Tov.
Yeah, I'll mail you guys a link to the presentation once it's ready.
Mm-hmm. And a pic of the new member of the family.
Thank you. I'll tell her. Okay, see you guys.
See you. Thanks a lot, Michael.